Shalom, my fellow Shrek enjoyers. Welcome back to another episode of Fun with Foos. It's been a while. I know. I know you're heartbroken to not be able to go over the the homeworks that you guys do in Econ 410. But I hope you had a good fall break. I went home. I listened to an interesting little talk from a former Polish president, and I came back to campus. It was like Saturday or Sunday. I pull up to Davis Library, and they're closed. Like it's like pulling up to a McDonald's and the ice cream machine's broken. Like what are we doing here? So I finally made it in on Monday at 11:37. There's always people outside these rooms too. They're busy. They have like a little kickback going. There are like 20 people on the 7th floor all doing their homework. They're roasting weenies together like it. It's nonsense. But without pre-gaming too much, I I haven't looked too much into this homework. But wait a second. Wait. Okay, we got a little transition going, and now we can just start. So I believe this one is about mostly uncertainty, which is this idea of deriving utility from things that we cannot fully contain. Like we don't know the outcome. So maybe it's it's an extension of, in the previous units, we're just like plugging in bundles and looking at the utility they provide. But what if we don't know the bundle? We got to figure out how to balance out that utility. There's also this stuff. I think maybe they're called extensions or something, about the substitution and income effect, that I'll give my 2-second spiel on. But I don't know how much wisdom I actually have. So when I read number 1, I am noticing that in this question, I would take note that we are demanding fewer hours of leisure, and so supplies more hours of labor in response to a wage increase. So if our wage increases, then effectively it becomes more advantageous for me to work. Like for every hour that I work, I am better off. So in my head, maybe this is not exactly the proper way you're supposed to be taught it, but this is how I remember it, and I think this is derived from my Econ 420 knowledge, which I assume most of you are taking after this class. So the substitution effect, and how I remember it, is this word substitution. Like when it becomes more advantageous, like this is the better thing to do, it is better to work now. So I want to substitute toward the better thing. So in doing that, I am going to work more hours. However, the income effect is this idea where, yeah, my wage went up, but like I could just keep working the same or less amount of hours and just be more rich. Like it's kind of this idea. This one is like, I remember it, the substitution effect is like the proactive person that wants to stay on top of it. And the income effect is like this lazy person that doesn't really care. But like, since their environment got better, like they're already kind of better off too. So how I would view this is, since they are demanding fewer hours of leisure, and actually I kind of like it phrased more here. I like this phrasing better, where we're taking more hours of labor. Then we are substituting the substitution effect. We are substituting toward more hours of labor because this wage is better off. So I believe that you are going to see that the substitution effect is stronger in this case, which would line up with A. And similarly, in number 2, we are going to see that the interest rate paid to savers increases. So if the interest increases, and maybe I'll write here, it's better. I was going to write better working. Okay, here you go. Better to work. I think you can kind of tackle any of these kind of income substitution effect conceptual questions with the same framework. So if the interest rate goes up, then it is better to save. And sorry, I think I'm just gonna sacrifice the the handwriting to save you guys some time. But it's better to save. So our substitution effect would say that I would want to save more because this interest, went up. So this voice is telling me to save more. And the income effect says that I can be lazy and I can save, not care. Not care. Okay, so as a result, Tom wishes to save less. So in this case, he's not saving more. He's not substituting toward the better thing. In fact, he's letting the income effect dominate. That he does not care. He wants to just keep his money as it is. He wants to keep spending. He is not going to take into account the new information we were just given. And he's just going to keep going with the flow. He's just going to keep doing the Tom thing. So it is in fact B, that the income effect is greater. And hopefully, to be honest, I still do not have an awesome understanding of the substitution income effect. But hopefully my intuition kind of makes sense. I was really pushed that that lazy narrative that Dr. Rourke, he'll hit you with you can work less, and there's all sorts of consumption smoothing or something. I couldn't tell you. It's out of my pay grade. But I'm just a 410 ULA. I'm not a 420. But now we got Noah. Okay. Oh, that's cool. I think that's probably a reference to a former ULA, Noah. But it was probably the same name when 2 years ago. I'm pretty sure this question, I've seen this question a million times. But essentially we have a utility function, we have Noah has some money, and we're wondering whether or not to play this lottery. So kind of the idea here conceptually is I want to think super broad. So if I am going to take part in a lottery, then I would want the utility of said lottery to be higher than the utility of no lottery. And just why that makes sense is obviously we're just going to go with the rational thing. So if the rational thing is it does not give me more than $25, then who really cares? I would rather just keep my $25 and call it a day. So what we are looking at is we're going to have we're going to calculate the expected utility. And what this is asking, it gives us this kind of generic P, where it's asking how much of a super awesome 900 buck bonus would we need to balance out that original 25. And I'll walk you through some of the things that I would think through in this problem. For one, I would say if I had a chance of winning $900 with a greater than 80% probability, then that would just be crazy. Of course I would take that over my original $25. And also interestingly, if it's less than, these don't really make sense to me. Of course, it's you want a higher probability. In these problems, the probability, you want it to be greater than 900. Because say P is, 0.001 or something, and we have no chance of getting 900. There's no point. So I believe intuitively, if you think about this problem, it has to be a greater than symbol. because less than symbol just doesn't really make sense in the way we phrase like the lottery should be bigger than not lottery. So we've already narrowed down this problem quite a good amount. And now really getting into the bread and butter of what this problem is. To calculate the expected utility of something, I'm going to plug it into this utility function. So I have 900 times P, because this is the probability. And then we're going to do plus, we have 100, because I'm just plugging in like the outcome of this and then plugging it into my utility. So that's what this expected utility means, is like I am just plugging in always this utility function, but weighting it with the probability of, whatever that outcome was. So in this case, it was 0.1. And let's put those in parentheses to make it a little more obvious. And this last one is, and a chance of not winning anything at all. So this would be, I believe, 0 times 1 minus 0.1 minus P. And this is just a little bit of intro probability stuff. Hopefully this concept makes sense. 1 minus, I basically just did like, this is going to happen in every case besides the cases where we won this 10% and this P%. But ultimately, since it's multiplied by 0, I think this guy just kind of falls off. So the expected utility of this thing, okay, so I believe is the square root of 930. I think it might be 30. So assuming that it is 30p plus 10 times 0.1, is that just 1? And then that is going to be equal, nope. So we want the expected utility to be greater than the utility of me not doing anything at all. So in this case, it was 25 bucks. So I plug that into my utility function, and we're going to get, I believe that's 5. So we're going to get 30p plus 1 is greater than 5. And then 30p is greater than 4. And then hopefully, is that just 4 divided by 30? Wait, I can get a little calculator. 4 divided by 30 is 0.1. Okay, p is greater than 0.133. That was just 4 divided by 30. I just put that over to the other side. And would you look at that? We got a little answer. So I think these questions are pretty formulaic. I think if you've seen this format of problem, you in a multiple choice format, you'll know that some of the inequalities just don't really make sense, particularly like the big ones or super small ones. And then from there, you're just kind of like getting some work on the paper to ensure your answer is in fact correct. And I think we get another very similar problem on number 4. So we have a von Neumann utility function. I believe, I'm not entirely sure what a von Neumann utility function is. I believe it's maybe an exponential function where like you plug in this thing as money or something. I'm not too sure. It's not that important. Don't stress out over what a von Neumann utility function is. Okay, so lottery 1, which statement is true? So I need to figure out, it's the same stuff where the expected utility of lottery 1 is going to have to be bigger than lottery 2 if I'm going to choose, whichever lottery. So I think we just get cranking. So we could get, oh, that's kind of interesting. Receive, I think I'll do lottery 2 first. That part's kind of tough. I don't know how to tackle that immediately. So if I just did 1600 at a 0.5 plus 400, so I'm plugging it back in the utility function. Remember, that's very important that we're finding the expected utility of lottery 2, that this is radical 1600, and then receive 400 bucks with a 0.5. So that is going to be 400 times 0.5 plus 20. Wait, no, not 400. It is going to be 40. I got a little ahead of myself there. Plus 20 times 0.5. But x. Okay, got it. So this x is what we're finding in the final problem. So this is going to be 20 plus 10. So this is 30. So I believe now we want to go back into lottery 1 and then see how do I get a expected utility of 30. Because that's going to be where we're kind of indifferent. Like I'm trying to find this pivot point as to where they're equal and like where they would separate. So I will try that strategy of going, so let's just call this x, and it gives us a 20% probability, 0.2, plus radical 900 with a 0.4%. We're running out of space. We're going to just go the other way. And radical 100 with a 0.4. So this is going to be 10 times 0.4, which is 4, plus 900 is 30. 30 times 0.4, is that something nice? 30 times 0.4 is 12. Would you look at that? So 12 plus 0.2x. And then I want that to equal 30. So we're going to get 16. I'm going to subtract that over. So we're going to get 0.2x is equal to 14. And then I divide both sides by 0.2 to get a terrible answer. Oh, okay, no, I got it. Okay, so x needs to be equal to 70. Now hear me out. And with the 70, that's the amount of utils this chunk needs to provide. However, it's asking us for the monies. So x in this case is the monies. So I'm gonna square it because that was our von Neumann utility function. So like I'm taking the post utility. That was a tricky one. That they tried to make you pick 70 because you would plug it in as utility. So like kind of what I'm meaning here is when I put it into the utility function, when I take the square root, then this is calculating the utility of what I got. So the utility of what I got should be 70, but then I need to remember to replug it into the little function, and x is going to be equal to 4,900. So all the conceptual stuff was there. I just almost got caught in the trap. And I think part C is a good trap. So I am going to lock in A as the final answer there. Beep, boop, boop, boop. Okay, more lotteries. Excellent. I think if I were giving a tip, I would just say whenever you see these little lottery things, just like default to calculating the expected utility of the lottery, and just remember, like, people make decisions based off of the utility of what they're going to get from a thing. Okay, So in this case, which lottery will she choose? I think it's just asking us which one gives us the most utility, which one is the most favorable outcome. So keeping her $8, then lottery 1 is just 8 to the 1/3 power, which is equal to 2. So we're going to get 2 utils from lottery 1, so maybe the other ones will or won't give us more than that. Lottery 2 is going to be give up her $8. Okay, so once again, we're just doing expected utility, which is equal to 0.2 times 1, and that is to the cube root. Remember, we're still plugging it into this utility function. Then I get my 0.3. And luckily, your teacher loves you so much that they give you nice little numbers that, that easily convert when you take the cube root of them. You generally don't even need the calculator. I need the calculator a couple times because I'm a doofus, but luckily most of the numbers are pretty chill on this homework. So plug in 27. Uh-oh, that's the cube root. Okay, and just locking in, set 0.2 times 1. That is 0.3 times 2, although I did just lie to you. the double back, I think you would want, maybe, I could do it. Okay, yeah, I can still do this. So that is equal to 0.2 times 1 is 0.2. 0.3 times 2 is 0.6. And 0.5 times 3 is 1.5. Don't need a calculator. I stand by my word. So that is 2.1 plus 0.2, which is 2.3, I believe, which is greater than 2. So we're definitely picking lottery 2 over lottery 1. But the question is lottery 3 even better? It's like Deal or No Deal, bro. We gotta open the we gotta open the last case. Okay, so expected utility of this last one. Then I am going to take blah 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 blah. Okay, so it's the same stuff. 1 to the 1/3 plus 0.6. This one seems to be worse off just on like a immediate glance because we have like a high concentration of the lame one instead of the 27, whereas on lottery 2 that one was super awesome. And actually, as a matter of fact, yeah, I feel confident in just getting to that part. So I'll write out the first step just to be kind of thorough, but I do not actually want to write out the whole work to save us some time. So what I noticed here is that this 0.6 is like the largest piece of this chunk, and it corresponds to 8, which is like not that much. Whereas on the lottery 2, the 0.5 corresponds to the big one of 27. So I'm like 99% confident without doing any of this math that this one, lottery 3, will be less than lottery 2. So that is why, I mean, I also have the answer key, so I can I can kind of fib, although I think that would be when I'm working out, I would realize that lottery 3 is not it. So we're going with lottery 2, baby. What was that guy's name? Howard? Maybe. He's bald. I know the guy on Deal or No Deal is bald. Howie Mandel? Is that his name? I could just be I could be making up whatever I want right now, and maybe you guys would believe me. Okay. So we're working on some insurance. So we have an instance of, okay, I believe how you do insurance questions is I can either take, what is the most? So the most I'm willing is we're going to go to that, that like little break even point that we did previously. So I could compare the utility of, so originally I'm going to have 160,000 and I'm going to pay this arbitrary I. And what this means is like, I would start with 160,000 bucks, but I'm going to lose the value of however much I pay for insurance. And that is going to be equal to the utility of me not paying for insurance. And whatever, when I write U, I think we're plugging it into this utility function is what I mean, at a 0.98% chance, because that is the 1 minus, like a common thing in probability that, I don't know, it makes sense, is like the total that you can have is 1. So I'm like, kind of maybe a way to reconnect the piece from earlier was if I did 1 minus 0.02, you get 0.98. Because like probability is just, it either happens or it doesn't. So we got our utility there. And then if we lost 70,000, then I would be taking the utility of 90,000 bones. That'd be a disaster if I lost all of my epic jewelry. It's like, what's a good movie? This is not a good movie. The Bling Ring is not a good movie, but it does have a similar plot of getting your jewelry jacked in Beverly Hills or whatever. Okay. So now that we have that, I'm going to plug in. Actually, maybe I don't know exactly how I want to do this, but the utility, is that 40,000? No, wait, is that 400? What's 400 squared? What's 400 times 400? I'm floundering. I don't have the mental capacity anymore. Okay, that is 400. So the thing is 4 times 400 times 0.98 plus, I would assume that is 300 times 4 times 0.02. And hopefully so that's 1600. 1600 times 0.98 is 1568 plus 1200 times 0.02 is 24. And then, come on, don't use the calculator. You know how to do this. Oh man, the trash guy is coming by. And he's coming to pick up my work, bro. Okay, that is 92. I think 1592. And I do see that as an answer. However, that's not what I am interested in. I am interested in whatever dollar amount. So I'm interested in this I variable. I'm trying to remember how to get that, because I do believe the answer is 1596. So if I did 4 times, is it just literally you take out that money and then I put it into, surely not, but maybe. So if I did, actually, I'll consult the answer key. I'll give my ego some rest and call it a day. That I too am fallible. Okay, that's how they do it. Awesome. That they simply just do 160,000. One more. Okay, and then they presumably take the square root of this thing, and then do they just divide both sides by 4 and then square it to get that number? And then, okay, that is kind of annoying. That I think that is proper protocol. I'll walk through what's actually happening here. So 1592 was like this break-even point that we wanted to find that this utility of taking the insurance has to be more than the expected utility from over here. So we're going to set it equal to that break-even point, and then I'm going to take the utility of this side and I'm going to solve out for this I. So that's what an insurance policy is. And it's kind of complex here. I know there are a bunch of steps. Really, it boils down to find the utility of this thing, set it equal to the utility of this thing, and then solve for I. Is kind of really all you're doing. And hopefully that isn't too hard. So then I'll just show one more time that this is the utility of left side, the utility of right side. We want them to be equal. So then we just do some basic algebra and then we solve for I. So I is that insurance premium that I would be willing to pay $1,596 so that I would not have to go through this gamble of maybe getting burglared. Like I would be, completely covered by my insurance policy. And for some reason we have some L's and K's thrown in. I have no idea what this guy is doing here. Potentially this is a Cobb Douglas. I think. I don't know if Cobb Douglas are the exponent has to be. I think the exponent's summed to 1, maybe possibly. But we'll solve it anyway. So labor exhibits a blank marginal product. So the marginal product of labor, if we remember, is just taking the derivative of this thing with respect to labor. So it's going to be 2LK squared. I believe so. We're just going to take that guy down since it's a coefficient, or it's multiplied together, that just stays. And then we're going to do DMPL DL because I am interested in seeing how this labor or how this marginal product is changing with respect. Oh wait, maybe do I even need to do that? Am I hallucinating right now? Labor exhibits blank marginal product. No, I do need, because it's asking increasing, decreasing. Yeah. I almost gaslit myself into not needing that. But if I just do this, it's going to be 2k squared, which is positive. So it's definitely increasing right there. And let's make sure, we're on a good track. And the corresponding isoquants slope downward at a blank rate. Okay, remember keywords here. Isoquants, I believe, are going to be similar to your indifference curves. So they're sloping downward at a blank rate. And when I see blank rate, that means we're looking at the curvature. And then if you remember back from like 3 Fun with Fooses ago, then you find the curvature by taking MPK. And we are going to get, 2KL squared. And then we're going to put we're going to solve out for an MRTS, which is equal to 2LK squared over 2KL squared. And that is going to get you equal to, processing. It's just K over L. Awesome. And the final piece here is I am interested in how this thing slopes downward. So I want to do DMRTS DL. And if I were to increase L, I'm just going to use some arrow math because I'm getting lazy. Just like the income effect. That would make this smaller. So as I increase L, this gets smaller. So that means I have a negative relationship here. And DMRTS-DK for capital is, if I make this thing bigger, then MRTS gets bigger. So they have a positive relationship. They go in the same direction. And then if I get a little graphy graph going, as my L increases, so as I go in this direction, as I go in that direction, my MRTS should be getting less steep. So it's going to look like one of them guys. Because I increase my L, so the slope is getting smaller. So I think we got, as we're moving, it slopes downward at a decreasing rate. Yeah, okay. That initially it's sloping downward at a big rate, like this slope is really big, and then it slowly decreases as I go in the left to right direction. And I also, just a little tip, we did left to right. So the reason why I made L go in this direction is because it said to go from left to right. We've had some trickers in the past of like, they asked me from right to left or some, you change up the K and we're like going up and down and stuff. Those are terrible. But I believe number 7 is C. We got an increasing and decreasing rate. And sorry, I'm a little sniffly. You guys missed like an entire saga. I almost died from from the cold. I think I don't know. Maybe my upperclassmen can relate. But whenever y'all freshmen pull up to campus, you bring plenty of viruses and disease that my body is not adapted to. Y'all are some biohazards, some biochemical weapons that we should put you on the front lines. But I think this is a very similar problem. So if I do, it says according to the MRTS. So that's probably a good indication that I should take why are we using M and R? Okay, whatever. So MP, sure, whatever, MM. MPM is, we're doing MPM over MPR, which is 3/4 processing, 3/4 of 4. Dude, I am struggling right now. That's just 3. That's just 3. So that's 3m to the negative 1/4, r to the 1/3. And then dish 1 is going to be 1/3, 4/3 m to the 3/4, r to the negative 2/3. Oh, brother, and then I have to do some fractional coefficient reciprocal stuff. This one is going to go down, that one's going to go up, so we got r over m, and then 4/3. So dividing by 4/3 is the same as multiplying by 3/4. 3 times 3/4 is 9/4, I believe. 9/4 r divided by m. Hopefully that made sense. I just kind of did like the Zach Galifianakis thing of like doing all the math in your head. Or that meme. Hopefully that meme conjured and me saying Zach Galifianakis didn't throw you off. So what are we doing here? We have a bundle. So let's plug that bundle in. And nope, wait, it was an R. Is an R a robot? Yeah, it's probably a robot. And then 3 units of raw materials. What is 9 times 8? 72. 72 divided by 12 is 6. 72 divided by 12 is in fact 6. So what that tells me is that our MRTS this specific bundle is 6/1, which is the same as our change in y. Our change in y was our r over our change in m. So if I were to change m by one raw material like it asked for in the problem, how many robots will it take? It'll take 6 robots because we already have that relationship. And if you remember, I think I talked about this like, a month or two ago. I always match up this format where it asks me like adding blank amounts of like more of raw materials. So I get this denominator to match up, and it already is, so that works. And then you just look at the corresponding thing up there. And if it said like 1/2, then I would divide that one by 2, and I would divide that one by 2. So the answer would be 3. That would be an arbitrary example if it was 1/2. But that's how I always tackle these. This problem is very similar to other problems that we've had in the past. And hopefully it would be free money if it's on exam. You've already done it. You've been here, done that. Okay, so on this one, we have a downward sloping convex isoquant. And I think all that means is that we got one of them puppies similar to earlier, where this is L and this is K. Oh, my tip, I think this is our first time doing L's and K's. This class just like repeats itself. Just replace X and Y with L and K, and like we'll throw in like economies of scale, and that's basically the only difference. We're repeating the class. The first half is just repeated in the back half, dude. So I believe what this means, we already talked about decreasing amounts of capital like up here, I think, or wherever we had it in the problem that I did. Yeah, right here. If we want to, think through this, then originally I'm giving up, like to get 1L, then it used to be like, I kind of did that a little poorly, the drawing. It should be a little more stable if I really want to show this effect off. But we've done the step pattern. Hopefully this isn't like something new to you. But this, so like if I wanted to get +1 of L, and then I did +1L over here, then this jump of K is like pretty big. However, this jump of K is like pretty small. Like what we'll notice, like that's a good chunk of change in K, and this is not much change in chunk of K. And I think normally she writes it out like, get some arrows or like some little dots, and these are like basically on the same dotted line. So that is what it means that we are giving up decreasing amounts. Originally we're giving up a lot of K, and then we're not giving up much K. So I believe this is true. I think I've walked through this a good amount of times. I don't want to, narc on this too hard. And then you need to be compensated with increasing amounts of labor to give up each additional unit of capital. So now we're just working in reverse. So oftentimes I like to literally just like flip your paper. So if I flipped the paper, then it would look something like that. And then I would write it like that, I think. Yeah. So it's the same. If I wanted each additional K, then like 1 unit of K over here is not the same amount as one unit of K. This is a bunch of L to give up each additional unit of K. Yeah. Okay, so like this labor is, processing. I don't want to, I want to just yap, but I believe this is a proper diagram. I'm kind of losing my chill. But the increasing amounts of labor to give up each additional unit of capital. Maybe I like that. I don't know, maybe I'll consult the key, see if it has any bright insights as we move along, blah, 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 blah. Maybe I'll, whoa, what happened? My other one just like disappeared. I normally keep them in this little top section. Can I just reverse it from this guy? Maybe my strategy was stupid. Compensate with increasing amounts of labor to give up each additional unit of capital. Oh, that's why. Okay, yeah, I was brain farting there. So to give up an additional unit of capital, dude, this is what I'm saying. They always trick you with the with the direction of this. So if we're giving up a capital, then originally I'm not giving up much labor. This is basically the same labor, and then that's a lot of labor. Bada bing, bada boom, we're done. This is true, and both statements are true. Lock in, twin. And okay, this is definitely a Cobb Dougie. If I were to, I think you guys have properties of Cobb Dougies from like homework 3 that will remain the same when they're L's and K's. I can assure you that they're still the exact same. However, I will very quickly think about this. So which one is false? Whatever, it's the same same logic that we always run. So output increases. So if I plugged in more L, if I made this bigger, does this thing get bigger? Yes, that is true. So that is not our answer. This thing is true. Do they slope downward at a decreasing rate? Convex. If you remember, Cobb Dougies always look like this. I'll use some plot armor and say that you know that. So that is not the answer. That is also true. The marginal product of capital increases as capital increases. So I did look at the key. I do like this one, and I will kind of explain it in terms of how it's done in the key. So the marginal product of capital is, what is it? B times LA to the KB minus 1, and that's just using a power rule. Yeah, I think that's what it's called in in calculus. So we're going to take DMPK because I am interested in seeing the, how it, the grade, the gravity of how much it's increasing or decreasing. So I need another derivative. And if I took this derivative, then I'm going to get B minus 1 times B, and then I do LAKB minus 2. And what's interesting about this guy is in the thing, it says that B is between 0 and 1. So if I subtracted this, then it's going to, but it can't be 0. Or 1. So like if I did 0.99 or something minus 1, like that's negative 0.01. Wait, nope, it's negative 0.01. There you go. So I can guarantee you that this one is a negative derivative, and thus it is not a positive relationship. It does not increase as capital increases. This would actually decrease. And remember, common thing that I've been trying to push to y'all is a negative derivative means it has an inverse relationship. So when I say this one increases, that means this one decreases. If I said this increases, then that means that one decreases. It's not just like inherently negative. It's not just everything is decreasing. It's that they're the opposite. And I really want to gel that in. But yeah, I think that is definitely a false, based on this cool idea that B minus 1 is inherently negative. And now we finally reach the long forms. So as per usual, I'll be taking the cheap route out because I'm a I'm a little jester. I just I go with the flow. So I think, but I will talk through this stuff. Oh, that is not what I wanted to go to. My pen is throwing me off. So what happens to the rate? Blah 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 blah. What I would just see is rate of giving up, rate, give up, left to right. We've seen this. It's the curvature. It's taking MRTS derivatives. You've seen this a million times. And then does labor diminishing marginal product. What that means is you take the marginal product and then you see the rate of the marginal product. And what that means is that we're taking the derivative of the labor. Bang. So that's what I would be looking at there. And then I would be taking DMRTS stuff on that one. And hopefully that is what the key also says to do. Yes, that is in fact what the key says to do. And hopefully you know how to take derivatives by now after doing a million of these problems and suffering through the first half of this class that we've gotten there. This expected utility one is kind of interesting. Although I think it's just another lottery. What is the maximum amount you could possibly lose? Although it is interesting. I think it's reversed from how we were doing it earlier, but I think the core kind of remains. Like, we are looking at the utility of taking a thing, and it's structured similar to the insurance premium thing, where like we're willing to lose an amount of money so that everything will go smoothly. But so if we currently have $9, then you plug the $9 into over here, and that's our utility, and then we're comparing it to, you know, our lottery situation. The minus A is whatever we're willing to lose, and then I just want it to be greater than. You follow this down with some algebra, and I don't know, it makes sense to me. What is going on here? 2.53. So this is the utility. This is the utility. We just added, or we multiplied it over. We squared both sides. That's why that's squared. And we then added A over and then subtracted the 6.25 to get $2.75. That seems to check out with me. And then, awesomely enough, you also got a free FRQ on this homework. I think people are making a big stink of it, and I would just say take the money and run. If you're given a repeat because your teacher doesn't do the due diligence of making sure they got a repeat, or maybe they did. Maybe MSA just wanted to give you guys a little bone on, if you realize that it's the same problem, then you'd get that. But we solved that earlier. It's 1596. Hopefully the insurance premium stuff made sense from 40 minutes ago, and now you're an enlightened goober. So I think that does it for the homework. I think the major takeaways are, for lotteries, do expected utility stuff and compare, like, you know, utility of whatever I'm going to do should be greater than the utility of whatever I don't want to do. That's how I always just kind of think about it. And there's only one help sheet for this. It explains what the difference between expected value and expected utility is. So I think the expected value of something is in like a monetary term, and utility is plugging into utils, like plugging the money into like the utility function that they'll always give you. And I think MSA also likes to push this idea of risk averse, which happens to be this little relationship right here, where the utility of whatever this was, so like if I plug in and I find the expected value of something, which is the same as the expected utility of something. I'm just like taking the 0.5, like whatever the probability was, and then just plugging in the literal money term instead of, taking, oftentimes we're doing like the square root in this homework, where I'm just plugging in the money. And kind of the idea here is that the utility of the expected value is not always going to be equal to the expected utility. So like if I took 76,000 and I plug that into the cube root, I don't know if it is equal to 40 or not. But what it means to be risk averse, somebody that doesn't like risk, or they're willing to give up additional stuff so that they will not take on risk, is this relationship. And I think pretty much the only time, actually, I don't even know when you really use this, but they might ask you on like a multiple choice question maybe, or something, maybe an FRQ, like, is this person risk averse? And in which case, in order to do that, I would take the expected value of something, I would calculate the expected utility, and then plug the 76,000 into utility function. And we covered this insurance premium problem. When I took this class, this help sheet was super valuable, and the help sheets are always like available. So like prior to me completing this homework, I would have looked at this help sheet and been like, man, there's, this thing that is very similar to my homework that I can just directly copy their steps on how to get I. I think the insurance one makes more sense to me. Like you take the thing, your initial wealth, you subtract whatever piece that you were willing to give up of that wealth to get insurance. This one kind of resonates in my head. I remember there used to be, probably on the FRQs of this homework, there used to be a problem about risk premium, and there wasn't a question about risk premium this time. If I were you, that question, it would be like solve for the risk premium and then also interpret it in context. And I remember that nobody really knows how to interpret what the risk premium is in context. I still don't really know what a risk premium is, to be honest. It's this idea that, like, I guess you're willing to give up to avoid risk. So in mentioning this like risk averse person from earlier, it is like how much risk aversion you have, and like what the monetary value of that is. And if you're ever asked a question about risk premium, I would highly encourage you just like memorize these steps. And if you're a risk averse person, then I would just like, I don't know, commit these to memory like the night before the exam. And like if there's probably like a 50% chance that there's an FRQ related to risk premium, or like some random little catch of a problem. And you can either be a risky person and not really care about this, and I don't really think you'll be missing out on much. But if you want to be safe and risk averse, then I would just go to this help sheet and I would memorize these steps for how to algebraically do it. It's really not that hard. To be honest, you just do the EV, you do the expected utility. Those are really not that hard, and then you just plug that sucker back into the utility function, and then throw a minus R in there, similar to how you did minus I. But that's neither here nor there. Okay, great. So I believe that is my time. I think we're how much time have I taken? Oh, almost an hour. We're sub 1 hour right now. That's not bad. So I'll give you my departing words. First, I want to give you your Polish word of the day. So your Polish word of the day is quite funny. It is a classroom object that maybe, how would I draw that? Whatever. I'll just draw it how a kindergartner would draw it. And then you got like a bunch of these little guys of little pages or something. But this is supposed to be my rendition of a notebook. And how you say notebook in Polish, it is zeszyt. Okay, so when you're thinking you got a notebook in class, you got your little notebook, you can point. Oh wait, I'll even add a little y there, or no, add a little line for my z. So how you pronounce this? This is z, and then the sz sound makes a sh, and then y makes an I sound, and then this makes a t sound. So when you're looking at your awesome notebook, you're like, this is a shit, baby. This is a shit. But that is your Polish word of the day. So zeszyt equals notebook. And there are plenty of funny introductory Polish words that we'll get to in the next few episodes of Fun with Foos. But that's your word of the day. I've been trying to bust down on my own language learning experience. I've been feeling very inspired, although I don't really have much time anymore, because the academic gods hold me captive and try to make me very sad and and want to crash out of UNC. But I hope you guys enjoyed. Hopefully you took away something from some uncertainty. It's basically the same as kind of the stuff you do in like a intro stats class, or like a ECON410 if you've taken that here. It's very similar stuff. But yeah, I don't have too much wisdom. I hope you guys have an awesome time, and welcome back to campus after fall break. Thanks so much.